Hey guys, hello everyone. Welcome to the San Academy once again. So guys, previously we had talked about chromium based oxidizing agents. We are continuing the discussion of oxidizing agents and we are going to today talk about manganese reagents. Okay, so there are a lot of reagents of manganese which are very popular. Most importantly, manganese based oxidizing agents are being asked in the manganese plus 4 oxidation state and manganese plus 7 oxidation state. So we are going to talk about all of them. We are also going to talk about silver based reagents which are popular. We are also going to talk about ruthenium based reagents. So in this particular video we are going to be talking about manganese and silver and ruthenium based oxidizing agents. If you are liking this series, please subscribe to the channel and also please give it a big like, right? And yes, we move onwards now and we start our discussion. So guys, see what is so important about manganese. When we are talking about manganese plus 4, that is MnO2. First we will talk about manganese dioxide and then about the triacetate. This one we'll talk about later on. So this manganese dioxide, this is black color solid and it is mostly soluble in the organic solvents. Okay. So it oxidizes allylic and benzylic alcohol to aldehyde and ketone. So this is the chemoselectivity part. This is the selectivity part that which we are valuing this reagent a lot because we want selectivity. Okay. So look over here, the first example. What do you have over here? See, in this question, in this example, you have only one alcohol, and that alcohol is an allylic alcohol. So fine, it is oxidizing the allylic alcohol to CHO, and itself it gets reduced to manganese plus 2. Okay, in the solution, right? So this was easy because there was only one alcohol. Now moving onwards, you see the second example. In the second example, you have a methoxy, you have a benzylic alcohol, and this is also having a double bond, but this is not allylic. It is one distance away, one carbon away from the allylic. So I would call this one as a homoallylic alcohol. Okay, so it is known as homoallylic alcohol, which is just one carbon away from a simple allylic, right? So who is going to be oxidized? The benzylic one, and as you see, this is so. And the other one, the homoallylic one, this is untouched. So this is the selectivity of manganese dioxide. It will prefer to oxidize allylic and benzylic alcohol over simple alcohols. And also, if there is a choice, it will first oxidize a 2-degree alcohol more than a primary alcohol. Okay, so this is the selectivity for the MnO2. Alright, that's it. Very simple. Now we will see more examples. What do you have? You have a diol over here. So when such a diol is present, how does MnO2 react with them? It is going to react with the diols. See, these are both secondary diols, right? But when they are converted to aldehyde, the bond is absolutely going to break. Okay, so when 1,2 diols are present, when vicinal diols are present, MnO2 is going to convert them into aldehyde, not ketone. So it is going to break the bond like this. Okay. So you also have to keep this in mind. Now, what are the other important reactions of manganese oxide? You see, there is a reaction called Core-Gilman Ganem oxidation, which converts aldehydes to esters. And now you see, it is such an easy reaction. When we have an aldehyde, directly converting this to the ester, it seems difficult because how are we going to do so? If we, let's say, we attack it from a methyl grignard, तो वो aldehyde का alcohol बन जाएगा. So what happens is, we are using manganese oxide and we are also using sodium cyanide, potassium cyanide. ये क्या करेगा वो देखो. So first thing, the cyanide is going to attack over the alcohol, the aldehyde, and that's going to give you cyanohydrin, isn't it? Common knowledge, aldehyde पे अगर cyanide attack करता है तो हमें मिलता है cyanohydrin like this. Now this cyanohydrin is because it is having a proton over here and an OH, and also it is on the benzylic position. So this is going to be converted by MnO2 to this kind of alpha carbonyl cyano group basically. So this cyano is as it is, and the alpha carbon is just converted to the ketone. Now you have a very simple replacement. Replacement by whom? Either there is methanol or there is ethanol, any kind of an alcohol. It is just going to do a nucleophilic substitution on the carbonyl carbon like this, and what happens? You are going to now get the ester because cyanide is a good leaving group, that's why. So this is an application of this MnO2 oxidation along with the allylic and benzylic oxidation. Definitely this is one more application. So you can convert a simple aldehyde to an ester or an alpha beta unsaturated aldehyde to an ester, keeping in mind that since the condition is not too acidic, it is going to tolerate the epoxide. You see in this example, you see there is MnO2, there is an OH group which is not allylic, it's just a simple alcohol. There is also an epoxide, so it is tolerating both of these groups, not touching them, only working at the CHO position. Why? Because directly we are not oxidizing, we are first converting the CHO to a cyanohydrin and then the oxidation is taking place. Okay, so more examples of this goes like this. See, you are having an allylic alcohol over here. Okay, in this particular example. So the allylic alcohol can be oxidized by MnO. So either you can start with a CHO. When you start with a CHO and you get the ester, that's the previous reaction, which is Gilman Ganem oxidation. Aldehyde से ester बना है, ठीक है. But what we can do is we can also go from the alcohol, allylic alcohol. MnO2 oxidation will give you an aldehyde first, which is simultaneously attacked by the cyanide. So you get the high, you are going to get the cyanohydrin over here, which is going to be oxidized by MnO2 once again to give this molecule, और ये हो गया है nucleophilic substitution on the carbonyl carbon to give you ester. So basically the application is the same. Okay. Now you have a three-membered ring over here, a strained molecule, but again MnO2 is only doing its job. It is only converting the alcohol to an aldehyde, and you know it's a secondary, it's a primary one, but also it is connected to a cyclopropyl group. So guys, the alkene and the cyclopropyl group, they are energetically the same, so the reaction is almost similar, right? Now in the last example, you see there are three alcohols. This is a primary alcohol, this is a secondary alcohol, and this one is a secondary and allylic alcohol. So naturally, which one will be oxidized if we are taking one equivalent of, or let's say the equivalent is not mentioned, but when you are having such a choice, you are definitely going to understand it is a chemoselective oxidation. So MnO2 oxidizes the secondary allylic alcohol to the alpha beta unsaturated ketone molecule in the presence of chloroform. Okay, so I hope that you understood what are the three most important applications of manganese dioxide. Now, first we see a little bit of manganese 3 acetate. You know, guys, because this manganese 3 acetate, manganese there is in +3 oxidation state. Now, this is not too much of an oxidizing agent, but this is giving you a very nice substitution reaction, and that also goes through radical mechanism. So, radical wise, it is important. Let's see what is it doing. Okay, so let's say you are already having a ketone. You already have a ketone over here. So ketone when reacts with the manganese triacetate, ये क्या कर रहा है? अल्फा पोजीशन पे acetyl ग्रुप को ऐड कर रहा है. कैसे ऐड कर रहा है? We will see that. So what happens is, if we have to do any reaction on the alpha position, we have to consider the enol. Goes without saying कि enol देखना पड़ेगा. So keto form से it has gone to the enol. ठीक है? After that, see, the oxygen is going to attach with manganese. One of the acetate group leaves. Let's say I'm writing it like this. The alcohol has become nucleophilic now. One of the acetate is leaving. so that you have one of the oxygen and manganese bond like this. अब एक acetate निकल गया, और जो ये cleavage हो रहा है यहाँ पे, this is a homolytic cleavage such that you are going to get radicals. किस तरीके के radical बन रहे हैं देखो, वापस से carbonyl बन जाएगा, alpha position पे radical आ गया. That radical is now going to this is one electron oxidation. If you realize, ये देखो क्या किया, ये जो एक radical है या एक electron है, what happens to that? That electron is being taken away by manganese acetate to become MnOAC whole 2 and OAC minus. एक OAC minus कैसे बना? पहले तो OAC radical था, because when this is attacking, one of the group is leaving, all right, there was one acetate group which left, and again if the electron is being taken away like this, if the homolytic cleavage is taking place, that one more electron is going to attack on one more molecule of manganese 3 acetate to generate one more acetate anion, and itself it becomes the cation. So it is one electron oxidation as well as substitution. So this is what you get. So what is this? One electron oxidation by the manganese 3 acetate, okay, and then it goes to do the alpha substitution also. So this is a specific reaction of manganese 3 acetate which I want you all to remember. अब इसका हम कुछ भी कर सकते हैं ना, इसको हम hydrolyze कर सकते हैं, all right, and we can go onwards and do any other reaction with this. So this is what you get. Now second thing, the manganese triacetate, when it is used in excess, can also do simple allylic alcohol oxidation like this in the 20 mole % of DDQ. तो ये एक reaction mixture है. अगर ये reaction mixture इस तरह से लेते हैं तो we can also cause the allylic alcohol oxidation just like MnO2. Okay, where the manganese there in +4 oxidation state. Alright, but then you have to use the excess of this. So this is how you understand कि ये सिर्फ एक electron का oxidation करता है and MnO2 does the simple alcohol oxidation. Okay. Now the most popular reagent of manganese is the KMnO4, where manganese is present in the +7 oxidation state. Okay, so before directly jumping into looking at the applications, you must know ये reaction हमने बहुत basic classes में देखे हैं, that manganese +7 KMnO4 while doing a redox reaction in the acid medium will accept 5 electrons, all right, to go from manganese +7 to manganese +2. ये होता है acid medium में reaction. Neutral basic medium में reaction होता है, takes away 3 electrons to go from manganese +7 to manganese +4. Okay, so the reactivity will also be different. First thing, under mild conditions, KMnO4 can affect conversion of alkenes to glycol. Glycol तक वो तभी रहेगा when the conditions are mild. When KMnO4 is taken in aqueous medium, because aqueous medium में it will itself be very powerful oxidant, it can cleave the glycol further to give you aldehydes. Okay, so careful control is required when we want to do only the dihydroxylation. तो dihydroxylation के लिए सिर्फ KMnO4 नहीं है, there are other reagents like osmium tetraoxide which we will discuss later on while we are discussing dihydroxylation. Right, so first one we discuss KMnO4. So alkene is going to form this kind of a cyclic intermediate. Okay, this is very important. Take care of this. A cyclic intermediate forms 5-member intermediate like this. After that, the proton loss from here, from one of the alcohol side, the proton loss is going to give you this kind of a alpha hydroxy ketone, या फिर इसको हम असाइलॉइन भी बोलते हैं, which will be further oxidized to the ketone. ये कब होता है? When the overoxidation is taking place. Also, when we are just doing simple hydrolysis in the presence of acid, then you get the diol. So you have to be very careful in carrying out these two processes, because the it's very easy for the manganese to do this kind of oxidation. So in the acidic medium, you are going to get this kind of a diol. Otherwise, in the basic neutral medium, it will give you overoxidation. ठीक है, अब मैंने आपको बोला इसको याद रखो, वाई, बिकॉज दिस विल हेल्प इन अंडरस्टैंडिंग स्टीरियोकेमिस्ट्री। जैसे कि ये मॉलिक्यूल है नॉर्बोनिन सिस्टम, इट्स द नॉर्बोनिन मॉलिक्यूल. So norbornene molecule, sorry, I had written H plus, it's going to be OH minus. Sorry, OH minus के presence में it's going to give you the diol like this. So you see norbornene system in the presence of NaOH and KMnO4 is going to give you a diol. Now, as I said, the stereochemistry is important because which diol? Is it going to give you the diol above या फिर exo या फिर endo? This is the endo one. This is the exo one. Both of the OH are pointing in the above direction, right? So which one is major? Definitely the exo is major. Why? Endo is not the major one. Why? Because it is going to form this kind of 5-membered intermediate from the less hindered side, right? ये less hindered side से ही attack करना पसंद करेगा. So that's why it is going to give you the exodiol. इस पे CSR net में question आ चुका है. The same question maybe in the past few years, that this norbornene system, we want exodiol as well as we want endodiol. We also want this endodiol. वो कैसे मिलेगा? वो हमें मिलता है Prevost and Woodward dihydroxylation. Mostly the Woodward dihydroxylation. I have already discussed that question. You can check it out in that video, and you can also revise Woodward cis dihydroxylation. Okay. Also, when we are to the same molecule, when we are providing KMnO4 in the neutral aqueous medium, absolutely it's going to break it down into dialdehyde. Okay. So that's what we have to be careful about. It's going to break it like this. Now we move onwards and we see कि aqueous medium में ऐसा क्यों होता है कि it is going to do over oxidation, right? Why does it do so? यहाँ पे हमने start किया है alkyne से. Okay, in the previous question we started from alkene and gave you dialdehyde. So alkyne से react करके first of all it forms the 5-membered intermediate. Then it is going to give you this kind of a diol as well as one double bond. Now this diol, you know, it's going to form the acylone. Acylone क्या होता है? Just alpha hydroxycarbonyl. That is acylone. Okay, so this is going to give you alpha hydroxycarbonyl first of all, and that will oxidize again to give you alpha diketones. This is how it goes through from alkyne to alpha diketones. Also, there is a major reaction कि KMnO4 in the aqueous medium, you know, it is very powerful in the aqueous medium. So it's going to break down the alkyne completely. और एक portion जो बन जाएगा इसका, ये जो CH है, this is going to be completely converted to HCOOH, as well as this side is also converted to COOH like this. So one of them could be formic acid and the other one is like this. So powerful is KMnO4. Similarly, many a times you will see कि जो benzene ring होती है या फिर let's say aromatic compounds होते हैं, तो जो side chain होती है, side chain oxidation is carried out by KMnO4, isn't it? So that is this reaction, side chain का oxidation. Okay, so I have written all the important types of reactions of KMnO4. Dihydroxylation भी है, alpha diketone formation है, then the cleavage of the alkyne, then the oxidation of the side chain. All right, all of these. Now we have seen one very important difference. Organic solvent में और aqueous solvent में क्या फर्क होता है? In the aqueous solvent, KMnO4 is more powerful because it is K plus and MnO4 minus. Alright, so you see in the aqueous solvent, it's just doing over oxidation all the time, right? But in the, you see, 3.3 mole KMnO4 benzene polyether and 1.0 mole KMnO4 in this ammonium chloride solution, right? So what do we see? We see it is converting this alkene to the diol as well as diketone like this, not breaking the chain anymore. ओके, यहाँ से पूरा ब्रेक नहीं कर रहा है टू गिव यू द कार्बोक्सिलिक एसिड और समथिंग, नो, it's only going to give you the diol and the diketone. All right, like this. Also, aromatic side chains, जो मैंने अभी आपको बता ही दिया था already, aromatic side chains will always mostly give you the acid. If that depends on the number of hydrogens. If you are starting with benzene, let's say CH3, like this. So toluene, sorry. So toluene is absolutely going to give you COOH. All right, and if you are starting with, yeah, you have seen this application, isn't it? When we were like studying the basics of KMnO4 oxidation, then only we have studied this one. Then you are going to get a ketone, and if there is only one CH, तो obviously oxidation नहीं होगा, ठीक है? Only the oxidation will take place for primary and secondary alkyl groups. Also, it oxidizes the amino compounds. This is very very important, क्योंकि हम बहुत बार ऐसे सर्च करते रहते हैं कि aromatic amine को या let's say aliphatic amine को भी कौन oxidize कर सकता है into nitro. So KMnO4 is the one who can do this job, amine to nitro conversion. Okay. Tertiary alkyl amines can be oxidized to nitro compounds directly, right? And this is the one, R3C. Why? Let's say अगर हमारे पास ये है, तो हम इसको क्यों नहीं ऑक्सीडाइज कर सकते हैं? Can we oxidize the carbon or the nitrogen? Like which one is going to oxidize? We're going to get a mixture of products. So that's why primary, secondary is not favored. Tertiary alkyl amines, because there is only this NH2 group to react, is going to be converted to nitro more specifically. Okay, I just hope you understand this point. Now, so in the previous example, it is already mentioned, already discussed कि ये heteroatom oxidation भी करता है. Now nitrogen is a hard center. Nitrogen से soft center भी present है, which is sulfide, which is the sulfur. So it can definitely do sulfur oxidation, heteroatom oxidation. So KMnO4 will oxidize the sulfur directly to sulfone. Addition of two groups. यहाँ पे इसका जो oxidation state है, let's say it was +2, here it goes to +6 directly. Very highly oxidizing in nature. Oxidation of terminal alkynes, which we have already seen that it's going to break down the alkyne, terminal alkyne specifically, into the carboxylic acid. Okay, this is just an example. Alright, so इतने सारे हमने अलग अलग टाइप के रिएक्शन देखे हैं for KMnO4, that what kind of reaction it can do. Now, yeah, examples of the same. Oxidation of the side chain gives you the acid directly. Oxidation of alpha hydroxy ester. See, this part is the ester, we cannot touch this. This is the hydroxy group. So alpha hydroxy ester in the KMnO4 and in the presence of a buffer. ये हम buffer लेना हमें जरूरी है to control the activity, and that's why you are going to get alpha carbonyl ester, or basically alpha keto ester, like this. Last but not the least, very very important, because this combination has been used many times. हम क्या कर सकते हैं, देखो हमारे पास KMnO4 है. So KMnO4 is popularly used for the conversion of alkene to the diol, but sodium periodate, we will also talk about it later on. Sodium periodate is used for the diol cleavage. It is itself very specifically used for the diol cleavage, sodium periodate. तो अब समझ में आ ही रहा है what are we using this for? Sodium periodate is going to cleave the diol that is generated by KMnO4. Okay, so यहाँ पे diol बनेगा and that is going to be cleaved. So you break it from here. This carbon is going to give you the acid, and this carbon is going to give you the ketone, like this. Okay, so that's what you're going to have. All right. Now the manganese, I have discussed the maximum types of reaction of manganese. Manganese +4, MnO2, then manganese +3, manganese triacetate, and then manganese +7, KMnO4. तो ये इतने टाइप के examples देता है. These are the types. More and more you will understand when you see more practice questions. आप जितने ज्यादा क्वेश्चन प्रैक्टिस करोगे आपको उतना ही अच्छा समझ में आएगा. And I will, once we have completed like a few reagent series, I will definitely start the practice sessions with you all. Now let's move onwards to the second type of oxidizing agents. So guys, ये भी थोड़ा सा important है, वैसे एक या दो बार ही आ चुका है, but still it is very very important. Silver based oxidizing agents, and I'm talking directly about Fetizon's reagent. Now who is a Fetizon's reagent? Fetizon's reagent is silver oxide, but on it's basically silver carbonate, not silver oxide, but on aluminosilicate like a zeolite. तो जैसे zeolite हमारा aluminosilicate रहता है, वैसे ही Fetizon's reagent भी है silver carbonate based on a aluminosilicate. Okay, what does it do? It oxidizes 1 degree and 2 degree alcohol to aldehyde and ketone, and prefers 2 degree oxidation over 1 degree, prefers conjugated over non-conjugated. तो ये same है just like MnO2, that it is going to prefer the allylic and benzylic OH groups over the non-conjugated ones, and also it's going to prefer 2 degree over 1 degree alcohol. Okay, so what is the mechanism guys? As I told you, it is a silver carbonate Ag2CO3 on cellite. What is cellite guys? जैसे मैंने आपको बताया zeolite जैसे aluminium silicate होता है, ठीक है. What does it do? ये देखो ये mechanism है silver carbonate Ag2CO3. So the oxygen is first of all going to connect to silver, which is a Lewis acid. Once it gets connected, it is going to do homolytic cleavage. Homolytic cleavage of the oxygen and silver bond in this way, and that goes through this kind of a proton removal from the carbon, and that proton is taken away by another water, or basically another oxygen from the carbonate. So if you also want to write it like this, it would be easier. See, if you want to write it in this way, although it is a radical process only, but just for the sake of understanding, आप इसको ऐसे भी लिख सकते हो कि ये जो O minus है CO3 का, CO3 2 minus का, this O minus is actually falling down over here, and the bond is going to take away a hydrogen, and it goes like this. This is just for understanding. Okay, this is the correct mechanism, but ये समझने के लिए है कि क्या बना यहाँ से कार्बोनेट का, एक CO2 बन गया है, एक H2O molecule बन गया है, because there was one negative and one hydrogen over here, so it's going to take away 2 protons. So H2O for this oxygen, and this oxygen is getting converted to the carbonyl, and Ag is going to be deposited as it is, the silver mirror. ठीक है, तो ये पूरा mechanism है Fetizon's reagent का, and this is how it works. You are having the, for example, in this first example, you are having the allylic alcohol. So we see the simple oxidation of allylic alcohol like this by the Fetizon's reagent. Okay, अब ये तो simple सा था, because there was no other choice. When we have a choice, for example in this one, when we have a choice, this is a secondary alcohol, this is a primary alcohol, it is definitely going to do the oxidation of secondary more preferred than primary. तो ये हो गया है chemoselective oxidation. One more very important thing, if the diols are on the 1 2 3 4 position, अगर diol 1 2 3 4 या 1 और 5 position पे हैं, 1 4 diol या 1 5 diol, if the position of the diols is like this, then after oxidation it's absolutely going to cyclize. Let's say Ag2CO3 ने एक alcohol को oxidize कर दिया है, and it has got converted to a carbonyl like this, for example. Alright, the bond is going to be over here, and one of them is oxidized, for example like this. तो ये जो दूसरा वाला अल्कोहल है ये अटैक करेगा यहाँ पे, the bond opens up. Now the ring which forms should be stable, otherwise the ring will not form. यहाँ पे ring नहीं बन रही है because it's like too small. here it is one oxygen, 2, 3, 4, 5. Since it forms a 5-membered ring, it is going to oxidize this OH which forms over here. It's first going to give you a lactol. ठीक है, और उसके बाद फिर से ऑक्सीडेशन करके ही ये लैक्टोन बनाएगा. So 1,4 and 1,5 diol will form lactones, 5-membered lactones, and here in the 1,5 diol it's going to form a 6-membered lactone. So this is one specific condition for the silver carbonate onselite oxidation. Now we quickly talk about very important ruthenium based oxidizing agents. So you must have seen ruthenium in two different forms. One is ruthenium tetraoxide RuO4, and sometimes you don't even see it directly because ये in situ formation होता है. It is formed in situ by mixing ruthenium trichloride NiO4 CH3CN CCl4 and water. So you don't see ruthenium tetraoxide much. Sometimes in the exam it is given directly, sometimes this combination is given. Okay, so this is one of them. The other one is TPAP. Yes, this is right over here. ये रहा ruthenium based oxidizing agent, tetra N propyl ammonium perruthenate. So we will also see this. We will see these two oxidizing agents of ruthenium today and see what are the types of oxidation they do. तो as I said कि in situ बनता है by mixing these reagents. So that's why it is given like this in the examination. Okay, sometimes also given directly. Let's see. प्राइमरी अल्कोहल का ऑक्सीडेशन करता है इनटू एसिड. प्राइमरी अल्कोहल ऑक्सीडेशन इनटू एसिड डायरेक्टली. Why? Because ruthenium is present in +8 oxidation state over here, very highly oxidizing in nature. But देखने वाली चीज ये है that it is alpha beta epoxy alcohol. So it's not reacting the epoxy group, which means that the mixture is not too acidic. क्योंकि epoxide is a acid sensitive group. Always remember कि epoxide तो acid sensitive group है. अगर acid नहीं है तो it will not be destroyed. So not a lot of acid is present to be able to destroy the epoxide. Hence it is tolerated. Tolerated matlab not affected by the ruthenium tetraoxide. Now, reaction of secondary alcohols, what will happen? So you have a lactone already over here and then you have a secondary alcohol. By this reagent, it will be converted to ketones. Just that. कोई ring break नहीं हो रही है, lactone part भी disturb नहीं हो रहा है, only the conversion of secondary alcohol to ketones. Very important. Such a strong oxidizing agent but also very chemoselective. ओके, व्हाट अबाउट द डायोल्स? डायोल्स किस तरीके से आगे बढ़ते हैं गाइज? इफ वी कंसिडर this with the osmium tetraoxide. So you know osmium tetraoxide does the diol formation. From an alkene, it does the diol formation. If we take it onwards, ये देखो vicinal diol है 1,2 diol. Now vicinal diols on reacting with ruthenium tetraoxide and NaIO4, specifically sodium periodate, that's going to give you this kind of a molecule, that is the acid. So what just happened, ये वाला जो OH group है यहाँ से, this got converted into the acid and this carbon has left. So one carbon less, you are going to get the acid in this way. एक कार्बन ब्रेक हो जाएगा यहाँ से. Similarly, we also see the oxidation of ether and phenyl group. ये अलग अलग टाइप के रिएक्शन है ruthenium tetraoxide के. Whenever you see an ether, it is going to give you alpha carbonylation in the ether because it's a very strong oxidizing agent. तो ये जो दो हाइड्रोजन प्रेजेंट है, दोनों को हटा के यहाँ पे दे देता है अल्फा, basically the carbonyl group which is going to form the ester. Right, and you see in another reaction, this is so beautiful. यहाँ पे आपके पास में diacetate है present on the 1,2 position, but it is not touching them. इसको सिर्फ उतना ही काम करना है जितना ही कर सकता है. So basically, this side also there is only one hydrogen, not interested. This side there are 2 hydrogens. So you get the carbonyl or you get the ester now. Similarly, look at this long ether chain. RuCl3NiO4 is going to convert this into an ester. वो भी carbonyl कहाँ add हो रहा है? On the more substituted side. Okay, very easy. Oxidation of phenyl group. So you see there is a R group and there is this benzene ring over here. Sometimes preferentially ये इस तरीके से अटैक करता है कि everything is destroyed and only you are going to get the RCOOH. All of this part of the molecule is going to be destroyed and you get only one carbon over here by the ruthenium based oxidizing agent ruthenium tetraoxide, okay, which forms in situ. So very important. Last but not the least, ruthenium का जो ये oxidizing agent है TPAP, that is tetra N propyl ammonium perruthenate. So it is perruthenate once again, but it is RuO4 minus, और minus को stabilize करने के लिए कौन है? Tetra N isopropyl. So there are 4 isopropyl groups ammonium perruthenate. ये इस तरीके से reagent है. Okay, very well. What does it do? A catalytic amount of TPAP with NMO as the co-oxidant. So I hope you remember NMO. NMO is N-methyl morpholine oxide. What's the role of that? It's a co-oxidant. कि perruthenate when it gets reduced, उसको फिर से oxidize कर देगा. So as a co-oxidant, oxidizes a range of functional groups. Let's see over here. So this example has an epoxide as I can see, और epoxide को फिर से touch नहीं कर रहा है because TPAP, NMO, DCM, none of them has an acid. So that's why the oxidation under neutral conditions are very important. The alcohol is converted to CHO and epoxide is not touched. Similarly, this alcohol is also converted to CHO and the protected alcoholic group is not touched. So it is very tolerating in nature. Tolerating मतलब कि सहन कर रहा है, नहीं oxidize कर रहा है, that is tolerating. Next example, this one taken from Caruthers. So you see catalytic amount of TPAP. So you have a primary alcohol. प्राइमरी अल्कोहल का ऑक्सीडेशन करता है एल्डिहाइड में, और जस्ट यहाँ पे थोड़ा सा डिफरेंस था इसमें, that ruthenium tetraoxide if you are taking primary alcohol to acid directly. So if I ask you that which ruthenium reagent will convert the primary alcohol into acid, it's ruthenium tetraoxide. And for TPAP, that is the perruthenate, it only converts to the aldehyde. So it's a mild oxidizing agent. उतना ज़्यादा strong नहीं है, mild oxidizing agent है, converts both the alcohols into aldehyde only. Now the same over here we see tolerates the acetyl group और OBN और ये double bond सबको tolerate कर रखा है, only just works at the primary alcohol to give you the primary aldehyde. Alright, so this is how it goes. And also let's see what are the tolerant groups to this particular reagent. Alkenes, it does not react. THP ethers, that is your tetrahydropyran ethers, it does not react. Epoxides, lactones, silyl ethers और indoles. ठीक है. अच्छा, THP ethers पे ये react नहीं करता है tetrahydrofuran type ethers पे, pyran type ethers पे, but definitely if we were taking RuO4, ruthenium tetraoxide, that would attack. So you see, you can compare the reactivities of two or more than two different metal oxidizing agents, and when it is asked in the previous years, you can also consider those examples. So this is what you're going to do. Just make notes and directly practice previous year questions so that you get more clarity upon the organic reagents. And I will also see you all in a similar class. और उस क्लास में हम और आगे जाएंगे और मेटल बेस्ड ऑक्सीडेशन स्टेट पढ़ेंगे. ओके, सो हैव अ नाइस डे. आई विल सी यू सून. बाय एवरीवन.